In Chapter 19, we're going to round out our discussion of equilibrium by talking about various aqueous equilibria, including buffers, titrations of acid-base, and the solubilities of sparingly soluble salts. To begin, we'll discuss buffers. Buffer is a fancy term for a solution that contains a Bronsted-Lowry acid and its conjugate base. In a buffer system, the addition of a foreign source of acid or base to the buffer results in a negligible change in pH because a foreign outside source of acid or base can react with one of the components of the conjugate acid-base pair. The theory behind how buffers work is predicated upon Le Chatelier's principle. In other words, in a buffer solution resists changes in pH in large swings because a buffer consists of both an acid, like acetic acid, and its conjugate base in solution. For example, a buffer might be prepared from acetic acid and sodium acetate, so that, to begin with, a solution that's a buffer of acetic acid and acetate contains some of this stuff, acetic acid, and some of this stuff, acetate, initially. Adding some foreign source of strong acid, like say hydrochloric acid, to a buffer results in this reaction proceeding to the left and consumes some of the acetate component of our buffer system. So long as we don't use up all of our acetate or all of our acetic acid, our buffer remains intact and the pH is largely unchanged. So let's do some definition work. A buffer is simply a weak acid and its conjugate base mixed together in the same solution. Or, alternatively, a weak base and its conjugate acid mixed together. And that's all a buffer is. A buffer is capable of resisting changes in pH when we add some outside source of strong acid or strong base to it. A strong acid generates H plus directly from its chemical formula. A strong base generates hydroxide directly from dissociation. The addition of a strong acid or a strong base to a buffer is met with reaction by either the conjugate base component or the conjugate acid component of the buffer system. A foreign acid, say hydrochloric acid, reacts with the buffer's conjugate base. In the acetic acid acetate buffer that we see above, the addition of HCl to that buffer would cause a reaction with acetate, C2H3O2 minus. And likewise, a foreign base reacts with the buffer's conjugate acid component. Again, in the buffer that we're using as a model up above, the addition of a foreign base, say sodium hydroxide, would react with the acetic acid component of our buffer. The HC2H3O2. So let's give an explicit example. Let's consider a buffer prepared from acetic acid, HC2H3O2, and sodium acetate, NaC2H3O2, to give us a presence of both an acid, this thing, and its conjugate base, the anion in the second compound, in solution. What's in our buffer? An acid, a weak acid, C2H3O2, and its conjugate base. C2H3O2 minus. We know that this substance is present because sodium acetate is a strong electrolyte and will completely dissociate. This is the contents of our buffer. How does our buffer work? It works by using the acid component, HC2H3O2, will react away any foreign base. And, alternatively, the base component, C2H3O2 minus, will react away any foreign acid. And therefore, whatever pH our buffer has initially isn't affected significantly by the addition of an outside or foreign source of base or acid. This is true to an extent, and we will talk about the makeup, characteristics, pH, and capacity of buffer systems as we move through the initial components of this chapter. So again, to prepare a buffer, we mix a solution that consists of a conjugate acid-base pair. When we mix a conjugate acid-base pair together, again, like acetic acid and sodium acetate, we create, by definition, a buffer. The acetic acid component of our buffer is capable of withstanding some foreign source of strong base, and the acetate component of our buffer is capable of withstanding the addition of some foreign source of strong acid. So long as we don't completely consume the acetic acid or the acetate component in this model buffer system, our buffer continues to operate because there continues to be the presence of both a weak acid and its conjugate base in solution. And that's all we need in order to define a buffer. To prepare a buffer, all we need to do is mix together a weak acid and its conjugate base, or a weak base and its conjugate acid from, say, two separate sources. To make an acidic buffer, we might combine a weak acid, again like acetic acid, and a source of its conjugate base, say sodium acetate. We'll talk about how we can adjust the pH to a desired final value. To make a basic buffer, we use a weak base and its conjugate acid. For example, we might combine ammonia, NH3, and the conjugate acid of ammonia, ammonium, in the form of ammonium chloride. Again, we can adjust the pH within bounds to certain desired values. All buffers maintain a more or less constant pH with the additions of some foreign outside source of acid or base to them. So then let's calculate what the pH of a buffer mixture must be. Suppose that we create a buffer simply by combining some 0.5 molar acetic acid with some 0.5 molar sodium acetate. We want to know the pH of this buffer given that the Ka value for acetic acid is 1.8 times 10 to the minus 5. And although we're not given volumes, we can still use concentrations directly because all we really need is to know the pH. That's the log of the concentration of H plus cations with a negative sign out in front of it. So we could set up an ice table that shows us something about how our acid, acetic acid, reacts in solution. It produces H plus cations when it dissociates and acetate anions, its conjugate base. The Ka value for this reaction is given as the concentration of H plus at equilibrium times the concentration of acetate divided by the concentration of molecular acetic acid. We can generate an ice table for this reaction and recognize that initially we have 0.5 molar acetic acid, but we also have 0.5 molar sodium acetate. The only thing that we have effectively zero of is H plus cations. We're going to ignore the contribution of the autoionization of water because it produces such a sparingly small amount of H plus. Therefore, this reaction will proceed in such a way that acetic acid generates some H plus. We lose X amount of this, gain X of our products. From these equilibrium concentrations, we can plug directly into our equilibrium constant expression and solve for X. Ka is equal to the concentration of H plus at equilibrium, that's X, times the concentration of acetate, 0.5, plus X, divided by the concentration of acetic acid, 0.5 minus X. The value for Ka that we're given above is 1.8 times 10 to the minus 5. At this point, in order to avoid solving a quadratic equation, we're going to make a simplifying assumption. We'll assume that X, the amount of hydrogen cation produced at equilibrium, is much, much less than 0.5. This seems like a valid assumption because by Le Chatelier's principle, since we start our reaction with both some acetic acid and some acetate, this reaction should generate a sparingly small amount of H plus cations by the time equilibrium is achieved. So, if we assume that X is much, much less than 0.5, then 0.5 plus X is for all intents and purposes just 0.5. So our numerator becomes X times just 0.5. And similarly, 0.5 minus X is for all intents and purposes just 0.5. So our denominator becomes just 0.5. And we end up with X equal to 1.8 times 10 to the minus 5. As with all assumptions, we should check to make sure that our assumption were valid. We check by calculating the percent dissociation. That's X over our formal concentration, HA initial, times 100. Here, alpha is equal to 1.8 times 10 to the minus 5 divided by 0.5 times 100. That's equal to 0.0036%, and because that is less than 5%, that's a good assumption. And we can keep this value of X, and we don't have to worry about solving a quadratic equation. So because we've been able to solve for X, we should be able to calculate a pH. pH is the negative log of 1.8 times 10 to the minus 5, which is 4.75. The pH of this acetic acid, acetate buffer, is 4.75. So this is the buffer pH. A buffer's pH will remain more or less constant even as we add some foreign source of acid or base to it. If we add some hydrochloric acid to this buffer, its pH will remain very close to 4.75 and won't decrease significantly. If we add some sodium hydroxide to this buffer, its pH will remain very close to 4.75 and won't increase significantly. So, let's think about an easier way to accomplish this same feat of calculating a pH for a generic acid-base buffer. We're going to derive a so-called Henderson-Hasselbalch equation that will universally be applicable to buffer systems. Because what we're doing in this math up above is setting up an ice table, ignoring the contribution of H+ production from our weak acid component, and using just the ratio of our conjugate base to conjugate acid concentration, we should be able to generalize those steps into a nice, neat formula that we can always use when we're dealing with buffers. The Henderson-Hasselbalch equation will be our governing buffer equation. So anytime we deal with buffers, we should use the equation that we'll come up with here. To derive the Henderson-Hasselbalch equation, we'll go back to a Ka value for a generic acid. In a buffer, we have both the intact molecular form of our weak acid and its conjugate base initially in solution simultaneously. What we're going to do here with this generic equation is just go ahead and take the negative log base 10 of both sides. We're going to take the negative log base 10 of our Ka value and the negative log base 10 of the ratio H+ times A- divided by HA at equilibrium. From here, we're going to use rules of logarithms to help simplify the right-hand side. Remember that if we take the log base 10 of a product like x times y, we can write that equivalently as the sum of logs. In other words, the log of the quantity x times y is the same as the log of x plus the log of y. We're going to apply that to the right-hand side of this equation now. We'll have on the left, negative log of Ka is equal to the negative log of, first I want to simplify this H plus L, plus the negative log of A minus over HA. Now, what we're going to do is recognize some of these terms as quantities we've already labeled with important symbols. The negative log base 10 of Ka is the pKa of an acid. And the negative log base 10 of H+ concentration at equilibrium is pH. I'm going to take one more step and transfer this entire term, the negative log of A minus over HA, to the other side so that I don't have to deal with any negatives at all. So I'll add that to both sides. And what we'll end up with as a final result is this. The pH of a buffer is equal to pKa plus the log of the concentration of A minus, which is the conjugate base component of our buffer system, divided by the concentration of HA, which is the conjugate acid component of our buffer system. Therefore, we can rewrite this term as the log of concentration of conjugate base divided by concentration of our conjugate acid. This is the Henderson-Hasselbalch equation, and it's a simple way to deal with the problem that we just solved up above. Let's use the Henderson-Hasselbalch equation to solve the problem of our acetic acid acetate buffer that we just looked at a moment ago. In the above example, we have 0.5 molar acetic acid, this concentration, and 0.5 molar sodium acetate, the base. The Ka value for acetic acid is 1.8 times 10 to the minus 5. We'll need a pKa, that's the negative log of that quantity. According to the Henderson-Hasselbalch equation, the pH of our acetic acid acetate buffer is the negative log of 1.8 times 10 to the minus 5 plus the log of the concentration of our base component, that's 0.5 molar sodium acetate, divided by our acid component, that's 0.5 molar acetic acid. If we carry through this calculation, what we'll find is that, sure enough, the pH of this buffer is 4.75. So next, what I want to think about is what's going to happen to our acetic acid acetate buffer if we add some strong acid like hydrochloric acid to it. Enough that we have an additional 0.02 molar H plus in solution just from our strong acid alone. Note that if we had just a 0.02 molar hydrochloric acid solution, the pH of that solution would be 1.70. But we're going to calculate what the pH of our buffer is after adding all that HCl to it. In order to accomplish this, we need to know what our strong acid reacts with. A strong acid, a foreign acid, reacts with the base component of our buffer. We need to be able to write a reaction that describes this acid-base interaction. H plus, this is from HCl, reacts with the base component of our buffer. That's the anion acetate, C2H3O2 minus. And the result of this reaction is the formation of HC2H3O2. This is another component of our buffer. The reaction of a foreign outside source of strong acid, like H plus from HCl, reacts with the conjugate base component of our buffer to generate an excess of the conjugate acid component of our buffer. This reaction does not reach equilibrium. It goes to completion. Our mantra is going to be that strong plus weak react complete. No equilibrium is reached when a strong acid is added to a weak base, or a strong base is added to a weak acid. Strong and weak react complete, meaning that we can use the same principles of stoichiometry from General Chemistry 1 to figure out what the concentration of our conjugate base and conjugate acid components of our buffer must be. Initially in solution, we have 0.5 molar acetate and 0.5 molar acetic acid. We add to this mixture enough H plus to represent 0.02 molar. Because this reaction goes to completion, there's no need to construct an ice table. All we have to do is identify a limiting reactant and use its quantity to establish how much of our other reactant remains and how much product is formed. H plus is present in the smaller quantity on the left-hand side, therefore it must be our limiting reactant. It's completely consumed and used up. It's completely consumed through the reaction with acetate. We use up 0.02 molar H plus and a stoichiometrically equivalent amount of acetate because the stoichiometry of this reaction is 1:1. So we must generate a stoichiometrically equivalent amount of acetic acid by the time this reaction has gone to completion. Strong plus weak react complete. We're left with 0 H plus from our strong acid. We've used up 0.02 molar worth of acetate, and we've generated 0.02 molar more acetic acid. Our new concentrations of our conjugate base and our conjugate acid are given here through this stoichiometry. And now, once again, we can use the Henderson-Hasselbalch equation to figure out the pH of this solution. The pH is equal to the pKa plus the log of the concentration of our conjugate base component divided by our conjugate acid component in our buffer. Again, the pKa is 4.75, the negative log base 10 of 1.8 times 10 to the minus 5. This time, plus the log of 0.48 divided by 0.52. If we carry out this calculation, we end up with a pH that's equal to 4.71. What this tells us is that our buffer's pH has not changed appreciably. It was 4.75 before we added hydrochloric acid to it. The pH of the hydrochloric acid that we added was 1.70, and the addition of that hydrochloric acid only changed the buffer's pH by 0.04 pH units. So what we've seen here is that the reaction of a strong substance, like a strong acid or a base, plus a weak substance, like the conjugate base or conjugate acid components of a buffer system, result in a complete reaction. A strong acid like HCl will always react to completion with a buffer's conjugate base like acetate. And we can use the limiting reactant and general chemistry 1 stoichiometry to calculate how much of an excess reactant remains and how much more product is formed. A strong base, likewise, will always react to completion with a buffer's conjugate acid. We can use the Henderson-Hasselbalch equation universally to work with buffer systems. The pH of a buffer is equal to the pKa of the conjugate acid plus the log of the concentration of the base component of our buffer divided by the concentration of the acid component of our buffer. The slide walks us through one more time the steps that we took in the previous example to calculate the pH of our acetic acid acetate buffer after we'd added 0.02 molar strong acid. So next what I'd like to do is a similar example, but replace the addition of strong acid HCl with the addition of a strong base, sodium hydroxide. To our original buffer that contained 0.5 molar acetic acid mixed with 0.5 molar acetate, we're going to add enough sodium hydroxide to represent 0.02 molar hydroxide ions in solution. We're going to think about our mantra, strong plus weak, react complete. In this example, it's hydroxide ion. This is a strong base. a strong base that comes from some outside source. So a foreign strong base. Bases react with acids. The only acid available for this substance to react with in solution is the conjugate acid of our buffer system, the acetic acid itself. Because this is a weak acid, this is our conjugate acid from our buffer system. Our reaction between hydroxide ion and acetic acid goes to completion. In an acid-base reaction, a proton is transferred. Hydroxide ion gets a proton from acetic acid and leaves behind the conjugate base of our acetic acid. Because this reaction goes to completion, we can treat it like we treat any general chemistry 1 reaction. We know that we started our buffer with 0.5 molar acetic acid and 0.5 molar acetate. We don't really care about water because water isn't an important contributor to the pH of this solution. The hydroxide ion that we've added from an outside foreign source of strong base had a concentration of 0.02 molar. So, it is present in the smallest amount, meaning that hydroxide ion in this reaction is our limiting reactant. It's going to be used up completely, and a stoichiometrically equivalent amount of acetic acid will be consumed, and acetate will be produced. So that by the time this reaction is complete, we have 0.48 molar acid left over. This is our new concentration of conjugate acid. And we have 0.52 molar acetate. This is the new concentration of our base. According to the Henderson-Hasselbalch equation, pH is equal to the pKa. Again, the pKa is 4.75 for this buffer, plus the log of the concentration of our base, 0.52, divided by the concentration of our acid, 0.48. If we carry out this calculation, we end up with a pH that's equal to 4.78. Again, not a significant change or deviation from the pH of our buffer before we'd added the sodium hydroxide to it. At this point, I'd like you to pause the video and calculate what the new pH of our buffer would be, assuming that instead of 0.02 molar, we'd added enough hydroxide to represent 0.45 molar in the buffer. And then we'll talk about the second problem after you've done that. To calculate the pH of our buffer after we've added 0.45 molar sodium hydroxide to it, we can take the same approach as before, knowing that we started with 0.5 molar acetic acid and 0.5 molar acetate in solution, and we're adding an outside source of hydroxide ion to it, in a concentration now of 0.45 molar. Again, hydroxide ion represents the limiting reactant, so it will be completely consumed, and a stoichiometrically equivalent amount of acetic acid will be used up, and acetate will be produced. So that by the end of reaction, we have 0.05 molar acetic acid and 0.95 molar acetate remaining. The acetic acid is our new concentration, 0.05 molar of our conjugate acid component, and the acetate, new concentration, is 0.95 molar for our conjugate base component. The pH of this solution is equal to the pKa, 4.75, plus the log of the concentration of base divided by the concentration of acid. At this point, the new pH is equal to 6.03, which is quite a big change from the 4.75 we'd had for the pH of our buffer before we'd added any base to it at all. This is 27% different from the starting pH of our buffer solution, but it's still not quite as high as the 0.45 molar hydroxide ion pH. Our pH has risen because we're starting to consume more and more of one of the components of our buffer. We're almost to the point of depleting our acid conjugate completely. And when our acid is completely consumed, we can by definition no longer have a buffer. So what happens if we add 0.55 molar hydroxide ion instead? If we'd added 0.55 molar hydroxide ion to our buffer system, what we'll see is that hydroxide ion is no longer the limiting reactant in this reaction. The conjugate acid, acetic acid, becomes our limiting reactant. It is present in the smallest quantity of our reactants, and so it will run out first. The conjugate acid concentration drops to 0. It doesn't matter what the concentration of our conjugate base is, because we have run out of one of the components of our buffer altogether, we no longer have a buffer. So if any buffer component runs out, we can by definition no longer have a buffer. The pH of the solution is dictated entirely by the amount of strong acid or strong base that is left over. So pH is governed only, in this case, by the concentration of hydroxide ions. How much hydroxide ion do we have left over? Well, we have 0.05 molar. We can calculate the pOH of a 0.05 molar solution of hydroxide ions and a pH by subtracting that from 14. The pH now is 12.70. We have strayed far from our buffer. This is 167% different than our original buffer's pH. At this point, we say we've overwhelmed the buffer and completely destroyed it. We no longer have a buffer because we no longer have one of the components that defined a buffer in the first place. A buffer is always formed by the presence of a conjugate acid-base pair together in solution simultaneously. If the concentration of either component ever reaches 0, then we no longer have a buffer. And the major species in solution at this point in this example was just hydroxide ion governing pH. So that leads us to the definition of buffer capacity and buffer range. What we saw in the previous example was that our acetic acid and acetate buffer could only withhold or withstand the addition of as much strong base as the concentration of acetic acid allowed. We say that the buffer capacity of a buffer system is the ability to maintain a more or less constant pH when a given amount of strong acid or base is added. The higher the buffer capacity, the more outside strong acid or strong base that we can add without significantly changing the pH. a significant change in pH is a difference of plus or minus 1 pH unit. The higher the concentrations of the components of our buffer system, in this example, acetic acid and acetate, the higher the buffer capacity of that system will be. The more acetic acid we had in solution to begin with, the more outside source of hydroxide ion that acetic acid could have withstood. A buffer range is that range over which the buffer is active. Again, we say that straying within 1 pH unit higher or lower than the pKa of the acid represents a suitable buffer. When we create a buffer, we want to choose a conjugate acid component that has a pKa very close to the value of the pH that we want for our buffer solution. If, when we add some foreign source of acid or base, the pH of our buffer changes by more than 1 pH unit, either up or down, we say that the buffer is no longer working desirably. It's no longer an effective buffer. So to prepare a buffer, we'll choose a weak acid or a weak base, and regardless of which we choose, the pKa of the acid conjugate will be within 1 of our target pH. We can use the Henderson-Hasselbalch equation to determine a ratio of the concentration of conjugate base to conjugate acid that will adjust the pH slightly, but by no more than 1 pH unit up or down in order to hit a target pH. The concentrations of our acid and base components of our buffer determine the buffer capacity. We'll pick a buffer concentration based on how much outside strong acid or strong base we would like our buffer to be able to withstand. All we have to do to make our buffer is mix together the appropriate concentration of conjugate acid and conjugate base. We could fine-tune the pH of that buffer solution by adding small quantities, drops at a time, of strong acid or base, and this is an experiment we would have done in lab this semester, but unfortunately won't be able to get to. So at this point, I'd like to talk briefly about titrations, because this is an experimental technique that often utilizes acids and bases and their reactions to identify the contents or concentration of an unknown solution. In analytical chemistry parlance, titration is a technique that utilizes a solution of known concentration in a burette that is added to an unknown concentration solution, like in an Erlenmeyer flask, in order to deduce something about the concentration of an unknown. Titrations can either be performed using color-changing indicators, like the one that we used in the laboratory earlier this semester to identify the concentration of sodium hydroxide solution, or can use potentiometric measurements based on electrical responses to generate a titration curve, which is the relationship of the pH of a solution that forms upon reaction of, say, an acid with a base as a function of the volume of known solution that we add to our unknown. In a strong acid, strong base titration curve, we might track the pH in, say, an Erlenmeyer flask that contains some unknown concentration of acid as we add base to it. The acid in this Erlenmeyer flask is a strong acid, say HCl, whose concentration we'd like to determine, and the base in this burette is a strong base, say sodium hydroxide, whose concentration we know precisely. Initially, before we add any base to this flask, the pH in the flask is significantly less than 7. Perhaps it's down here. As we add small quantities of base to that flask, the pH doesn't change appreciably. Remember, this acid is strong, and so there's a vast quantity of H+ in solution. Eventually, though, we react all of that H+ away, and our pH changes sharply. It rises to 7 and then quickly beyond. Eventually, this pH will level out as we add more and more hydroxide ions. In this titration curve, we have one key feature. When we have an equivalent number of moles of base to moles of acid, we reach the equivalence point. Here, at the equivalence point, the number of moles of acid are equal to the number of moles of base. And therefore, in a strong acid, strong base reaction, we produce just plain old water. The pH at the equivalence point for a strong acid, strong base titration is always 7. In order to perform this type of titration, we would need to have some potentiometer, like a pH meter, constantly monitoring the pH of solution as we add more and more base to it. If we don't have that type of instrument available to us, we can still perform a similar experiment using, instead of a potentiometer, a color-changing indicator, a chemical compound present in solution that's not contributing to the pH significantly, but will change color as the pH changes. A good color-changing indicator for a strong acid, strong base titration curve is the substance phenolphthalein. Phenolphthalein changes color from colorless to pink as the pH rises above 7. We can use phenolphthalein as an indicator to help us track when the pH of a solution that is a result of mixing an acid and a base has reached 7 or beyond, and so can indicate the end point of a titration experiment. There are lots of color-changing indicators that change color over certain pH ranges that are useful for not only strong acid, strong base titration reactions, but also for the reactions of weak acids and bases. We have used phenolphthalein this semester to track the progress of an acid-base reaction for strong acid, strong base reactions. Many other color-changing indicators exist, though, and will change color at the pH of our equivalence point for different types of weak acid or weak base titrations. Generally speaking, when we titrate a weak acid with a strong base or a strong base with a weak acid, we get significantly different looking titration curves. Of note, we'll never titrate a weak acid with a weak base or vice versa because things would just get too complicated. So we'll only consider 2 scenarios here: adding a strong acid to a weak base, or adding a weak acid to a strong base. In the first example, when we add a strong base to a weak acid, we can imagine a titration curve whose pH starts below 7 but not appreciably slow. A weak acid has a higher pH starting out than a strong acid, simply because it doesn't generate as many H+ cations in solution as a strong acid would. The addition of a strong base to a weak acid causes an initial rapid jump in the pH of our weak acid because it consumes all of the scant H+ cations that are there in the first place. As we add more and more base, though, our pH is going to level out. It levels out because the addition of strong base in small quantities to a weak acid results in the production of the conjugate base of our weak acid. The presence of some conjugate acid and its conjugate base partner in solution is by definition a buffer, and buffers resist changes in pH. So in small additions of a strong base to a weak acid, we end up with an early buffer region. And until this buffer is broken, the pH stays more or less unchanged until we get to a sharp equivalence point. At the sharp equivalence point, the pH rises rapidly. But then as we add more and more strong base, it's going to level off. There are two key features of this titration curve. One is a buffer region where we have some weak acid and its conjugate base in solution simultaneously. As hydroxide ion from a strong base reacts with a weak acid, it generates H2O and A-. The presence of these two things in solution, while hydroxide ion is still a limiting reactant, results in the formation of a buffer. What's more is that the equivalence point, the halfway point of this jump, or the inflection point along this curve, has an equivalence point pH that's greater than 7. At this equivalence point, the moles of hydroxide ion, our base, are equal to the moles of our weak acid HA. So we consume completely all of our HA and all of our hydroxide ion, leaving water, but also some conjugate base. The major species in solution is A-. A-, the conjugate base, acts like a base would. Bases have pHs greater than 7, and the equivalence point pH for a weak acid, strong base titration, is greater than 7 because of the presence of that conjugate base, A-. Eventually, as we add more and more hydroxide ion, the pH levels out based on OH- concentration. Adding a strong acid to a weak base just sort of flips the drawing that we made up above. When we add a strong acid to a weak base, we can imagine that the pH initially, before we add any acid, is greater than 7, but not appreciably so because weak bases don't raise the pH as significantly as strong bases do. The addition of some small amount of strong acid to this weak base causes a rapid decrease in pH as all of the hydroxide ion concentration is completely consumed. After which point, our acid reacts only with the intact form of our base, forming a buffer. As that buffer is broken, the pH drops sharply and has an equivalence point less than 7. Eventually, the pH, after we've added enough acid, levels off as dictated by the concentration of H+ from our strong acid alone. In this titration curve, we get a buffer region That mirrors the titration curve we saw above. But in this case, we're adding some H+. From a strong acid to a base to generate conjugate acid. In this reaction, the presence of both a weak base and its conjugate acid, by definition, result in a buffer. At the equivalence point, we have an equal number of moles of H+ as moles of base. And the only thing left over in the solution here is the conjugate acid, Hb. As an acid, this substance works to lower the pH of solution. The equivalence point of a weak base, strong acid titration, will always be less than 7. Hence, if we want to track either a weak acid, strong base titration with a color changing indicator, or a strong acid weak base titration, we need to choose an indicator whose color changes close to the equivalence point value, dictated by whichever conjugate species, either conjugate base or conjugate acid, predominates in solution at an equivalence point. To round out our discussion of equilibrium and finish chapter 19, we're going to spend a little bit of time talking about solubilities. In General Chemistry 1, we learned solubility rules and how to identify when a substance will be soluble versus precipitate. But that was one of the small lies that we told in General Chemistry 1 that we're going to address now. Like a weak acid, a salt that's insoluble is just one that simply doesn't fully dissociate into its ions in aqueous solution. Instead, it only gives up a limited quantity of ions per every mole of formula unit or intact compound. And it turns out that some things that we have claimed are insoluble can actually be quite a bit more soluble than others. For example, we said that iodides are soluble unless they're with silver, mercury, or lead. What we're going to do here to introduce this concept is compare the solubilities of lead 2 iodide and mercury 1 iodide. To do so, we're going to write out a reaction that shows what happens when an insoluble salt is placed in water. In solution, lead 2 iodide is generally insoluble. In General Chemistry 1, we would have written its phase as solid, even when mixed with water. But that doesn't mean that no ions are produced whatsoever from lead 2 iodide. It just means that a small quantity are. In this small quantity, an equilibrium is achieved, where lead 2 iodide dissociates into lead 2 cations and iodide anions. To be stoichiometrically precise, we make 2 iodide ions for every 1 PbI2 formula unit. We express this equilibrium with an equilibrium constant that gets a new special symbol. This is KSP. A KSP is a solubility product equilibrium constant. For this reaction, we can write down an expression for the KSP of PbI2 by taking the quantities of concentration of our products raised to their stoichiometric coefficients, concentration of Pb2 plus times concentration of I minus squared, and divide by any aqueous or gaseous reactants. Here, our sole reactant is in the solid phase, so we don't include it in our equilibrium constant expression. Like we've tabulated values for equilibrium constants, for general equilibria, for acids, and for bases, we so too can calculate the equilibrium constant for solubility products. For lead-2 iodide, the value of KSP is equal to 8.5 times 10 to the minus 9 at 25 degrees Celsius. All KSP expressions will show us how an insoluble substance dissociates its ions and establishes an equilibrium with those ions in solution. For example, Hg2I2 can be written to show a similar equilibrium with the dissociated cation, mercury 1, which is the oddball, Hg2, 2 plus 2 iodides. The KSP expression for mercury 1 iodide looks like Hg2, 2 plus concentration times I minus concentration squared. And it has a tabulated value, a KSP, of 4.7 times 10 to the negative 29 at 25 degrees Celsius. So, while the KSP for lead-2 iodide is on the order of 10 to the minus 9, for mercury iodide, that KSP is 20 orders of magnitude smaller. Hg2I2 is by far less soluble than PbI2 because its equilibrium constant is so much smaller. This suggests that there are far fewer ions produced from Hg2I2 at equilibrium than there are from PbI2 at equilibrium. The more soluble of these substances is PbI2. On the basis of comparison of the KSP, the solubility product equilibrium constants, for these two substances, we say that PbI2 is a much more soluble compound than Hg2I2. We can work with KSP values, set up and solve ice tables for sparingly soluble salts in the same way that we've done work with equilibrium for all of the substances we've encountered so far. In the equilibrium for PbI2, dissociating into ions that we drew on the previous slide, we have a KSP value that's equal to 8.5 times 10 to the minus 9. What we would like to know is the concentration of these ions, lead and iodide, in 1 liter worth of water containing some PbI2. Presumably, we'd place enough PbI2 in solution that we're not going to have to worry about this substance being limiting because it produces such a scant amount of ions anyway. So the presence of just some PbI2 in solution will generate some ions, Pb2 plus and I minus. But because PbI2, our reactant, is a solid, we can ignore its concentration in our ice tables and our equilibrium constant expressions. Before any of this PbI2 starts to dissociate, we have 0 lead ions, 0 iodide ions in solution. Some of this PbI2 solid starts to dissociate and we gain a stoichiometrically equivalent amount of Pb and a stoichiometrically equivalent amount of iodide, carrying down the coefficients from each. So that at equilibrium, we have X amount of lead, 2X amount of iodide. In our KSP expression, we know that KSP is equal to Pb's concentration at equilibrium times iodide's concentration at equilibrium squared. And that this KSP has a value of 8.5 times 10 to the minus 9. At equilibrium, the concentration of Pb is x, the concentration of iodide is 2x, and that whole quantity gets squared. So that from this term, we get 4x squared when we square it. 4x squared times x is 4x cubed. We're going to solve for x here. X is equal to the cube root of 8.5 times 10 to the minus 9 divided by 4. Or, for this problem, 1.3 times 10 to the minus 3. X, according to our ice table, is the solution to the concentration of Pb at equilibrium. The concentration of iodide is worth 2x. I minus concentration is equal to 2x is equal to 2 times 1.3 times 10 to the minus 3, or 2.6 times 10 to the minus 3 molar. And from here, we get the concentrations of both of our ions, lead and iodide, in an aqueous solution of a mixture of lead-2 iodide with water. We can carry out a similar calculation to determine the concentration of mercury 1 and iodide from Hg2I2 in a mixture with water. So at this point, I'd suggest you pause your video and try that for yourself. Here's our ice table worked out for Hg2I2. Notice because of the stoichiometry of the formula and the reaction, we're going to work out an identical expression to the one we had before. The KSP expression is the concentration of mercury 1 times the concentration of iodide squared. The value for KSP for Hg2I2 is 4.7 times 10 to the minus 29. Concentration of mercury 1 at equilibrium is x, of iodide is 2x, and that quantity gets squared. So that 4x cubed is equal to 4.7 times 10 to the minus 29. In solving for x, divide both sides by 4, then take the cube root. X, which according to our ice table is the concentration of mercury 1 at equilibrium, ends up being 2.3 times 10 to the minus 10. And 2 times x, which is the concentration of iodide according to our ice table, must therefore be 4.6 times 10 to the minus 10. These ice table solutions are important. It turns out that according to the terminology associated with solubilities, the solution for just regular old X from these ice tables we've just constructed, either for PbI2 where X was 1.3 times 10 to the minus 3, or from Hg2I2 where X was 2.3 times 10 to the minus 10, these solutions for X are called the molar solubility for a salt. So this is the molar solubility of Hg2I2. It tells us how many moles worth of ion, one formula unit worth of an ionic compound can produce per liter of water. The molar solubility for PbI2 is 1.3 times 10 to the minus 3 molar, and the molar solubility for Hg2I2 is 2.3 times 10 to the minus 10 molar. We give the symbol S for molar solubility. Given the molar solubility for a salt, we can derive the KSP for it. For example, the molar solubility of PbSO4, lead 2 sulfate, is 1.4 times 10 to the minus 4 molar. So S is 1.4 times 10 to the minus 4 molar. And the molar solubility is the solution for X in an ice table. So if we construct an ice table for PbSO4, anywhere we see X, we can plug in 1.4 times 10 to the minus 4 molar. Lead 2 sulfate is a sparingly soluble compound that produces lead 2 cations in solution and sulfate anions with a 1-to-1 stoichiometry. The KSP expression for this equilibrium is concentration of Pb2 plus times concentration of SO4 2 minus at equilibrium. An ice table for this reaction looks like this. We ignore our solid material reactant. We initially have 0 lead, 0 sulfate in a solution of lead 2 sulfate. So we produce X amount, a stoichiometrically equivalent amount of each, and have X amount by the time equilibrium is established. The KSP for this reaction is the concentration of lead 2, X, times the concentration of SO4, X at equilibrium. The KSP is X squared. Our molar solubility tells us that anywhere we see X, though, we can plug in this value 1.4 times 10 to the minus 4. So in this expression down below, the KSP is equal to X 1.4 times 10 to the minus 4 molar squared. This works out to be 1.96 times 10 to the minus 8. The KSP for PbSO4, therefore, must be 1.96 times 10 to the minus 8. It might seem intuitive to you that adding an acid to something makes it more likely to dissolve. But why is that? Well, it turns out that if a sparingly soluble salt, something that doesn't normally dissolve fully on its own, has an anion that's a Bronsted-Lowry conjugate base of a weak acid, the addition of a strong acid to that solution increases the solubility of the insoluble compound. This is due to Le Chatelier's principle and the effect on equilibrium. For example, calcium fluoride is an insoluble compound. In an equilibrium expression for calcium fluoride, CaF2, calcium fluoride produces calcium cations and 2 molar equivalents of fluoride anions. A KSP expression for this reaction takes the calcium cation concentration, multiplies by the fluoride concentration squared. The molar solubility of calcium fluoride in just plain water, just pure water, can be determined by setting up an ice table like we did for our previous examples and calculating the result for X. We ignore solid in our ice table and initially have 0 products. We produce X amount of calcium and 2X amount of fluoride, so that by the time equilibrium is established, we have X and 2X quantities of each, respectively. The KSP value for this compound is 3.9 times 10 to the minus 11, and that's equal to the expression calcium concentration which is X, times fluoride concentration, which is 2X, quantity squared, at equilibrium. X times 2X squared is 4X cubed. If we solve for X, we divide by 4 and take the cubed root of both sides. We end up with 2.14 times 10 to the minus 4 molar. This is the molar solubility of calcium fluoride in pure water. Next, what we'll do is calculate the solubility of calcium fluoride in a solution of acid, perhaps hydrochloric acid, at a concentration of 0.05 molar. Again, it seems intuitive that in an acid solution, calcium fluoride ought to be a little bit more soluble. We should expect that this substance dissolves to a larger extent when we mix it with acid rather than just pure water. But why? Well, let's set up our ice table again and think about what we have in solution if we mix calcium fluoride with 0.05 molar acid. So we'll revisit this equilibrium one more time. Calcium fluoride dissociating into calcium and fluoride ions. But this time in an acidic solution. In an acidic solution, an acid doesn't have any propensity to react with calcium, but could potentially react with fluoride. We know that hydrofluoric acid is a weak acid because it is not one of our strong acids. Hydrofluoric acid has a Ka of 6.8 times 10 to the minus 4, as given above. This substance can be reacted with H plus cation ions to make a weak acid, HF. That process looks like this reaction. Fluoride ions that are produced from calcium fluoride react with H plus cations that were already in solution because an acid is present to form the weak acid, HF. This weak acid could dissociate back into H plus and fluoride, so an equilibrium gets established here. The Ka value for HF was 6.8 times 10 to the minus 4. But in this reaction, we have reversed the direction of a normal acid dissociation. Anytime we reverse a reaction, our reversed reaction's equilibrium constant is equal to 1 over the equilibrium constant of our normal reaction. In this case, reversing an acid dissociation. The equilibrium constant for this reversed form of our reaction is 1 over 6.8 times 10 to the minus 4, which is equal to 1.47 times 10 to the positive 3. So our equilibrium constant for this reaction, let's call it reaction number 2, is 1.47 times 10 to the positive 3. We can also write down an equilibrium constant expression for this reaction. The expression looks like the concentration of HF divided by the concentration of fluoride and the concentration of H plus at equilibrium. As a good approximation, since we're dealing with a strong acid, we know that the concentration of H plus is 0.05 molar. So this equilibrium constant, with a value of 1.47 times 10 to the 3, is equal to HF concentration over fluoride concentration times 0.05 molar, to solve for HF in terms of fluoride concentration, we ultimately end up with 73.5, 0.05 times 1.7 times 10 to the minus 3 times fluoride. To account for all of the fluoride ions produced by calcium fluoride, the total number of fluoride ions are wrapped up either in the fluoride in HF or in the fluoride produced from CaF2. All of the fluoride in the solution is either from HF or from calcium fluoride. The fluorides that calcium produces plus all of the fluorides that are wrapped up in HF is given by concentration of fluoride plus 73.5 times the concentration of fluoride. That's how much is wrapped up in HF. This is the total fluoride concentration. The ratio between no acid in solution, in a neutral solution, relative to in an acid solution, looks like this. Fluoride ions without acid present relative to fluoride ions with acid present. The ratio is 0.0134. So what this means is that by the time equilibrium is established, because we're pulling away some fluoride ions, by Le Chatelier's principle, we have to be funneling more calcium and more fluoride to the product side from our calcium fluoride in order to compensate for that loss of fluoride. Our KSP expression looks like this. KSP is 3.9 times 10 to the minus 11. That's equal to X, the concentration of calcium, times 0.0268X, the concentration of fluoride, squared. Solving this for X gives us the following result. X is equal to 3.8 times 10 to the minus 3. This is the molar solubility of calcium fluoride. Now, granted, we took a lot of liberties with the mathematics here, so I won't ask you to go through a mathematical problem like this one on your own. Instead, the moral of this story is that to encourage dissolution, we add acids to materials to, by Le Chatelier's principle, force a reaction to create more products. This is the take-home that you should know from this section. In the next section, we'll do a calculation that you should understand how to perform. This deals with a similar aspect called the common ion effect. Instead of trying to dissolve calcium fluoride in, say, a solution that contains an acid, imagine that we tried to dissolve calcium fluoride in a solution that contains either calcium or fluoride already. The presence of a common ion, an ion in common with ones that calcium fluoride is trying to produce to reach an equilibrium, will, by Le Chatelier's principle, force our reaction from proceeding towards products. The presence of a common ion will lower the solubility of calcium fluoride. So, let us calculate the solubility of calcium fluoride in a 0.1 molar solution of sodium fluoride. So, we're going to place some calcium fluoride into a beaker full of solution that already contains 0.1 molar NaF. We're going to put some solid CaF2 into this beaker and imagine what happens. As we do so, we can once more write out a KSP expression for calcium fluoride. We can draw an ice table. In our ice table, we'll once more ignore calcium fluoride solid. We'll have 0 calcium cations to begin with, but this time in solution, we already have some fluoride initially. It's from sodium fluoride, yes, but it's there nonetheless. The initial concentration of fluoride ions from sodium fluoride is 0.1 molar. Ignore the stoichiometry of this reaction. We know that we have 0.1 molar fluoride ions in solution already, even before calcium fluoride starts to dissolve. Calcium fluoride will dissolve to a small extent though, because it needs to produce some calcium. So that at equilibrium, we have X amount of calcium ion and 0.1 plus 2X amount of fluoride ions. In our KSP expression, 3.9 times 10 to the minus 11 is equal to the equilibrium concentration of calcium, X, times the equilibrium concentration of fluoride, 0.1 plus 2X, quantity squared. In order to solve this problem, we're going to make a simplifying assumption. We have seen so far that X is really small. X is on the order of 10 to the minus 4 or 10 to the minus 3. And therefore, even 2 times X, when added to 0.1, is going to, for all intents and purposes, to as many sig figs as we can muster, be 0.1. We're going to assume that 0.1 plus 2X is effectively the same as 0.1. What that would mean for us is that we don't have to solve a cubic equation. X times 0.1 squared suffices to solve this problem. To solve for X then, we just divide both sides by 0.1 squared. When we do so, we get 3.9 times 10 to the minus 9 molar. Where fluoride ion were already present in solution of sodium fluoride, when we try to get calcium fluoride to dissolve in that solution, its solubility is inhibited 5-fold, 5 orders of magnitude over. So the molar solubility with common ions in place and NaF is equal to 3.9 times 10 to the minus 9. The effect of a common ion, by Le Chatelier's principle, inhibits this reaction from going forward as much as it did in the 2 previous examples, in pure water and in acid solution. And one last comment on this concept. We can use the KSP value for a sparingly soluble material to predict whether or not a precipitate will form upon mixing 2 solutions. So we can quantify now, rather than just use solubility rules, to definitively state whether a precipitate will form when we mix things together that might form an insoluble compound. For example, when 0.1 liters of a 0.003 molar calcium nitrate solution is mixed with 0.2 liters worth of a 6 times 10 to the minus 6 molar or 6 micromolar sodium fluoride solution, do we still get a precipitate? We have a really small quantity of fluoride ions reacting with calcium nitrate. This is a metathesis or double displacement reaction. Back in General Chemistry 1, we might have written our reaction to look like this. Calcium nitrate is mixed with sodium fluoride to produce calcium fluoride, which could precipitate in sodium nitrate. The net ionic equation for this reaction would have eliminated nitrates and sodium ions as spectators. We would have been left with Ca2 plus 2 fluorides producing calcium fluoride. We know now that this is an equilibrium process, that solid calcium fluoride could regenerate ions of calcium and fluoride in solution through an equilibrium process. Once again, we can set up an ice table. In this ice table, we'll need the initial concentration of calcium ions after we've mixed this solution together. So, what we've effectively done is diluted calcium. The dilution equation, M1V1 equals M2V2, says that if we know our initial concentration of calcium and our initial volume of calcium, that we can calculate its new concentration after we dilute it to some final volume. The final volume we've diluted to results from a mixture of 0.1 liter with 0.2 liters. We're going to assume that volumes are additive so that we have 0.3 liters of total solution at the end. For calcium, M2 is 0.001. We can do something similar to calculate fluoride ions concentration initially upon dilution, and we end up with 4.0 times 10 to the minus 6. We don't care about concentrations of our solid, so all we really need to do is determine whether or not these concentrations will result in our reaction proceeding towards products or staying reactants. We won't have to work through the rest of this ice table to figure that out. So, what we'll do is determine the equilibrium constant for the reaction as it stands right now. This is the reverse of a reaction that we wrote on the previous slides, where calcium fluoride dissociates into its respective ions. And anytime we reverse a reaction, we have 1 over our equilibrium constant. Our equilibrium constant for calcium fluoride was 3.9 times 10 to the minus 11. So this reaction has an equilibrium constant that's given as 2.6 times 10 to the positive 10. Our job is going to now be calculating Q, a snapshot of this reaction at this point in time, just as we've mixed some calcium and some fluoride together. Q for this reaction is given in the same way that K would be. The reaction quotient for this reaction would be the concentration of any products, but there aren't any products of use in an equilibrium constant expression or reaction quotient because our sole product is a solid, divided by the concentration of our reactants raised to their stoichiometric coefficients. The concentration of calcium is 0.001. The concentration of fluoride is 4 times 10 to the minus 6, and that gets squared. Multiply those two things together, we end up with 1.6 times 10 to the minus 14. 1 over 1.6 times 10 to the minus 14 is 6.3 times 10 to the positive 13 power. Right now, our equilibrium constant expression, 2.6 times 10 to the minus 10, is smaller than the reaction quotient for this reaction written here. Because Q is large, that means that we have too many products and not enough reactants. Remember, if a reaction quotient is big, that means that products outweigh our reactants. Therefore, no more products would form, and therefore no precipitate would form. A more succinct way of saying this and accomplishing the same thing without having to go through the slog of this mathematics is that if we just multiplied together these concentrations and the result was smaller than the KSP for the substance we're interested in, then a precipitate will not form because the concentrations of the ions aren't high enough yet. And conversely, if Q is greater than or equal to a KSP, a precipitate will form because the concentration of precipitating ions are in excess. Let's use that more simplified approach to arrive at the same conclusion. So, what we'll say is that from these concentrations that we calculated from dilution earlier, the equilibrium constant, KSP, and the reaction quotient Q can be written in the same way. Calcium concentration times fluoride concentration squared. Here, Q is equal to 0.001 times 4 times 10 to the minus 6, quantity squared. 1.6 times 10 to the minus 14. We'll next compare Q versus our KSP. What we find is that Q is less than our KSP. Q is small, meaning that we don't have enough ions yet in order to make a precipitate form. So, anytime Q is small, there are too few ions to form a precipitate. That means that if we mix together a solution of 0.1 liters containing 0.003 molar calcium nitrate with a solution of 0.2 liters containing 6 times 10 to the minus 6 molar sodium fluoride, even though our general chemistry rules might have told us that a precipitate forms, we don't see any evidence of precipitate yet. So there would be no precipitation in this reaction, even though Gen Chem 1 might have said otherwise. The concentration of ions simply isn't high enough yet to generate the precipitate calcium fluoride.